We have Marilyn Matz and Alex Poliakov from Paradigm 4 to talk about SciDB for scientists who want to do science, not computer science. Thank you.
Go ahead, start. Sorry.
Hi, Paradigm
I just have
4 is the
PowerPoint
company,
crashing.
and the product is
PowerPoint
called
itself.
SciDB for Science Database. The science guys were doing big data and big computation and complex analytics before the rest of the world even got there. So this is a completely innovative new kind of database. It has two goals. The first goal is to provide efficient storage and access for all of the new kinds of data that's being generated today, like genomic sequencing data, timestamps, data coming from sensors and instruments, image data, and graph data. Our thesis is that this new kind of data is structured data, and it's an unnatural act to cram it into a relational database table model. Also, if you want to really efficiently access the data, you want to get it out of data lakes. Who's ever found a pair of glasses when they drop them into the ocean? You can't find things in the data lake. And you want to get it out of file systems, and you want to be able to do the analysis right on the data in the native data storage format. A lot of the interesting analytics that people are doing today are basically linear algebra operations to complex analytics like principal component analysis. And so what we've done is build a linear algebra engine for working on all of this new kinds of data. And we've been able to do it in a way that is massively scalable. So I'm going to, if you slip one more slide, SciDB, we've been selling and servicing as an open source community, the science world and the commercial world. I'll just do two of them real fast so that we have a demo prepared for you. The NCBI 1000 Genomes browser, which is a brilliant browser for exploring variant data in populations, has been running on our open source SciDB database for 2.5 years now. And lots of folks in climatology, metagenomics, and commercial folks in precision medicine. Our founder is Mike Stoneblaker out of MIT. He's one of the forces behind many of the major advances in the database world, starting with Postgres, and more recently Vertica, one of the first columnar databases, and now Paradigm 4. And there is an open source community edition that's available at SciDB.org. It's an extensible database, and the company Paradigm 4 provides proprietary extensions. And with that, let me switch it over to Alex because we're short on time.
Wow. Hi, everybody. Thanks for having us. I'll try to be brief. It's a bummer we're short on time, but I encourage folks to check out our website, check out our videos, and check out our many other demos. So SciDB is a distributed database that is unique in that it organizes data in arrays instead of tables. It allows users to run complex analytics in the database, and it is programmable from statistical packages like R, Python, and soon MATLAB and Julia. So that, and it runs on commodity hardware clusters or in the cloud. So I like demos a lot more than I like slides. So we have for you, just really briefly. You can't, ooh, oh, this is so bad. Nope. Oh, wow, this is, wow, this is, here, how's that? Now, there, I fixed it. And there's my skull, all right. All right, hold on, just a second. That's really a bummer. And well, what are you gonna do? It's I got this. Hold on. Best for VGA display. Let's scale it. Okay. All right, how's that? Is that better?
Good, yeah.
All right, we are making progress. So I have a machine that's running in EC2. I told you that SciDB is a distributed database, but here I am running only a single node in EC2. So this thing will not perform as best as it can. I have here an R script that connects to the database and issues queries and visualizes the output. This is data collected from a NASA MODIS satellite. So this is a satellite-mounted radar data that is looking down from the satellite on the Earth's surface and reading altitude positions at various places on the Earth's surface. So here there's a spattering of green dots and orange dots, and the orange dots are of a higher altitude than the green dots. So this is a very abstract data set direct from the satellite loaded into what we call a SciDB sparse array. It is natural to represent this as organized by latitude and longitude. And you'll notice that this is a rather sparse data set. If I were to zoom out, I would get even more dots and even more white space between them, and I can't really make out the features of the image. So here's a more complicated query. How many of you people have worked with this RStudio interface before? All right, so this is somewhat the right audience, right? So just keep in mind, I'm not running these things in R directly. I am programming SciDB from R, right? So I have loaded the SciDB R package, which is on CRAN, and my R code gets translated into SciDB queries, and those queries then get run on the database, and the data is then downloaded back into R as arrays or data frames. So I will call this draw regrid function, which splits this sparse array into squares and computes an average altitude for each square, and now I get a denser image. So now this looks a lot more like an actual map. Any geography buffs here know what is there at longitude 113 west and latitude 36.5 north?
The Grand Canyon.
Yes, that's the Grand Canyon right there. Very, very, usually people don't know. That's very cool. Yeah. So I can also say, you know, lat equals to, let's say, 35, zoom equals 1.5, and this will adjust the parameters of the query so that the regrid computation takes a smaller sample of the data set. And so here I've zoomed in on some mountain, right? I can also join this with a public data set and say find San Francisco, and it will first query one array which has locations of cities, and then it will query another array, which is this MODIS data graph, and it will find San Francisco. It will find me an average elevation for some sampling of it, and it will plot it. So here I've built Alex's maps, as I like to call it, with SciDB, with only a couple of days. The amount of code here is 95 lines total of R code. And then, you know, there's some more code to load the data and build the database. So, gee, it's already 11:24. I'll do an ultra fast spin through these slides. Okay, so we allow you to create two-dimensional or n-dimensional structures that look like this. This is how you might organize stock trade data. All right, so stocks traded at a particular time. You can have nullability of attributes, and you can have empty cells altogether because there isn't going to be a trade every millisecond for every equity. Once you have data organized this way, you can do fast slicing. So when I called the draw function and I quickly pulled out a subset of the geospatial data, that was a very quick, what we call a between operation. Give me a subset of an array, and you can do it by indices. And then you can, of course, do aggregations and summary statistics. And then, of course, you can take the data, compose it into a dense matrix by, say, converting the time axis into minutes. You can then multiply this matrix by its transpose, which is the most computationally intensive step to compute a correlation matrix. And then now we have a plot. So this is a plot that was computed using SciDB for stock trades, where we are showing stock symbols that are highly correlated with each other. So the prices correlate, right? So here's all the Wall Street banks together in a cluster. There's JP Morgan, Goldman, Bank of America. Here's all the tech stocks, Apple, Amazon, Microsoft. Here's Walgreens and CVS together. Here's a cluster of Japanese companies, interestingly enough, right? So now if I have this kind of, you know, we've skipped the regularization step and so on. Now that I have this matrix, I can make money, right? When one of these things goes up, I can bet on the other one, right? And I can make a profit. So this is the kind of offering that we have, is a database that allows you to have array data stored and these kinds of array computations and array analytics. And of course, as soon as you do it for somebody, this is what they tell you, right? You did it for stocks, great. Now do it for all the options, right? This is just the kind of world we live in. And the scientific data is everywhere. So this is an example of how you would organize a cancer data set for different measurements for different genes and samples. How many folks here work in bioinformatics? Okay, so there's a few. So I have a demo towards the end to show you. The architecture of SciDB is essentially a shared nothing cluster, a network of commodity nodes running in this proverbial cloud. The cluster is really quite decentralized. You can connect to any of the processes and then issue your query. And then that process shall become the query coordinator for that query. And these are all the various connection options. What's not shown here is there's also a C++ interface, as well as a web-based interface, a JavaScript-like thing. So you issue queries to the database, and the nodes talk to each other and present you with the result. The attributes in the storage are decoupled. So in this case, the prices will be stored separately from the volumes. The data is organized in rectilinear chunks like this. And the rectilinear chunks are then split among all the storage instances using a hash function, so that a query that only asks for the price will not have to read the volume data from the disk. There is also an option to store a region of data around each so-called chunk, so that window computations can be run quicker. In terms of computer science, this is important because I can essentially tune the system so that overlapping and window queries take a lot less time and essentially become embarrassingly parallel. The organization model allows us to do those quick multi-dimensional lookups, right? So if you have data in multiple dimensions like stock and price, or if you have data in dimensions like latitude and longitude, and you need to quickly pull out a square or a strip, I quickly know which chunks I need to look at. And so lookups by dimension axes become very, very quick. And it also turns out that this kind of data organization is very good for linear algebra. And linear algebra is often what you need to compute those kinds of key high-performance analytics. So as far as the analytics, we offer dense and sparse matrix multiplication, generalized linear models, distance metrics, clustering algorithms, and this is a set that's expanding and growing, and we are adding new algorithms to this set, and members of the community are also adding new algorithms because we're an open and extensible system. So remember, it's a database, so it has transaction support and multi-user support, so you can have somebody writing to an array and somebody reading data at the same time, and things don't get don't get corrupted, we hope. Soon there will be elasticity added so that you can just add more nodes to the cluster and grow it in vivo live. We have an array versioning support so that every time you change an array of data, you can go back in time and look at what the data looked like at a particular point in the past. And it's important to say a few things about what it's not, right? This is not something that's built for text analytics. This is not something that you would load books into and try to run analytics over text. This is built for structured mathematical array data and scientific computation. One of Stonebreaker's big points that he often makes is that one size does not fit all in big data. And so this is an engine specifically built for scientific computations, and we don't claim that this is going to be the best solution for everything, but it's going to be a very good solution for a certain set of problems. Also, you know, since we're on the cusp and we're on the intersection of the SQL world and the scientific computing world, right? We're between the standard SQL engine and something like R, right? So we have a language problem that we need to solve, and we solve it by making the database programmable from R, and that works well. But some folks are telling us, well, we need SQL, and we like SQL, and that's the thing that we use, so SQL. And other folks are saying, no, SQL sucks, and we are scientists, and we like to work with matrices, so give us matrices, thank you very much. All right, that's just I think, the reality of the market, and that's one of the problems we have to deal with. And I also need to mention that SciDB is highly extensible. Right? So there are plugins that are add-ons to this thing that we provide, and there are plugins that other folks out there have created and have provided. So among some of the interesting ones, RExec is something that will launch an R interpreter on every instance, and so if you have some piece of R code that you want to run in parallel on the data, you can use RExec to do that. K-nearest neighbors, sure. Super Fun Pack is something one of our developers was, you know, called a pack of interesting and useful functions. So that's, you know, we do some cowboy stuff sometimes. There's, as far as things provided by the community, so there's a library for working with HTF5 data in SciDB. Some of our friends from the genomics world have created a loader for the 1,000 genomes data into SciDB, and they've created a genotype user-defined type. Somebody wrote something called TensorDB, which is a package to use SciDB to do tensor algebra. And this set is hopefully growing, and we like to engage the scientific community and add more and more functionality to this thing. So, cool. I did in 15 minutes what I was hoping to do in 30 minutes. I don't know how much of that was communicated and sunk in, but now for the cool demo. So this is the cool demo. This is what I wanted to show. How many of you guys have heard of the 1,000 Genomes Project? All right. So I have loaded and there are many ways to organize variant data in SciDB. When I say variant data, it's data about how human genomes differ from each other, for those of us who aren't in bioinformatics. So I have loaded data on this small EC2 nodes. This is just 2 of the chromosomes. So my variant array looks like this. Oh boy, this resolution stuff is really killing me. So these are known cataloged genomic variations from the set. So this is chromosome 21, and you know the human genome is an alphabet of 3.5 billion letters long. Each letter is C, T, A, or a G, and it's 2 chromosomes. So you have a copy of 2 copies of this alphabet. And so when folks deal with bioinformatics, they don't really store the whole alphabet per person because that's unnecessary, because any 2 genomes will be some 99% identical. So we only pick places where the genomes are different and we store those places, and those places are called genomic variants. So this is an example. So on this chromosome, on this position on the chromosome, so it's like a coordinate that's going from one end to the other. Some folks have an A and some folks have a C with some statistics about it, right? This is how we reason about the genetic data. The 1,000 Genomes Project currently has 2,500 samples from different places in the world that have been analyzed for these variants. And so here's a simple query: is given a particular variant on chromosome 21 at this position, an AT turns into an A, and I want to know how many of the samples in my data set have this variant. So I run that, and the database returns only 4. So this is a very rare genetic variation. So only 4 of the samples have it. We have in the genotype structure two attributes, one for each chromosome, because you have 2 copies of each, right? So this is a very rare feature. Not a lot of samples out there have this. So some of these will be very frequent, and some of these will be very rare. So the demo we've done with this data is we've organized this data, first picking out the most frequently occurring variants. So those with a frequency of above 55% or so. And then organizing a matrix inside SciDB that looks like this. So it's just a number for whether or not a variant was present or not, a 1 or a 0, and it's organized by a variant ID and a sample ID. So on these 2 chromosomes, we have 2 million different variants, roughly. So that's 2 million sites at which there was a difference recorded in any of the samples. And then out of those, we pick 34,000 variants that are frequently occurring. And we did this selection process in the database as well. And so we build a matrix that just looks like this. So it's organized by sample and variant, and it's just a matrix of 0s and 1s. So there's some slop in how the data was organized. And the first thing we did is we created a covariance matrix here. And with R, I can plot a visualization of the covariance matrix and have it, a downsampled image displayed on the screen. So there's that. Zoom in. All right, so now this is a sample by sample measure. And each pixel in the matrix represents how close those 2 samples are as far as the presence and absence of these frequently occurring variants. So we thought this was a very cool plot because this is showing us that there's some structure in the data. There are these regions here where the measure of distance between the samples is low. The samples are closer to each other than others. What do you guys think that means? Your thoughts? The fact that we have groups of people who are closer to each other than others genetically. Ethnicity, right? So this is the math essentially showing that. And then we thought, well, this was a very cool plot, so we also computed the principal components on this data. And here's a very cool 3D plot of the principal components, right? And this is something I can rotate. This is all our stuff, right? The selection of the frequently occurring variants was done in SciDB. The math was also done in SciDB. The whole process took about 10 minutes to compute. And now in R, we can have this, because R is very good at visualizations and these types of things, right? So now in R, we have this nice image we can spin around. And then we use the k-means clustering algorithm to assign a color to these 3 clusters. And if I show you this table here, so the columns are the population assignments that the data had for these different samples, And the rows are the clustering assignments that the k-means came up with based on our math. So we see that red is almost exclusively East Asian, and blue is almost exclusively African, and green is a mix of American, European, and South Asian, right? So we've essentially been able to pull out the ethnic groups using some math in SciDB in just a few minutes of computation, in fact, on this small EC2 machine. You know, obviously, if you were to do a similar computation on, say, cancer genomic data, you might find that there are different subtypes of cancer, and some of those subtypes might respond better to a particular therapy than others, right? This is one possible practical application of this calculation. Okay? So this is what I wanted to show you. So it's 11:40. Thank you very much. I wanted to take some questions from you.
We can take some questions. Thanks for the very interesting talk and excellent job keeping the time.
Yeah.
So, but well, maybe while the panel gets ready, we can take a few questions. Anybody?
Everything was perfectly clear.
It was very clear. It was a very.
All right.
Well, thanks for the whole morning. All the speakers were were all very interesting with a wide variety of topics. We covered everything.
Thank you. Okay.
Yeah, for them.
Oh, just a minute. They have something for you.
On the behalf of Academy of Science and Engineering, we want to acknowledge and appreciate today's keynote speaker. I request Dr. Justin Jan to give away this keynote, these certificates to Marilyn Matz from partnership. Yeah, he's also there. And Alex.
Thank you very much.
Dr. Justin Jan.